Hello everyone, welcome to this webinar on introducing HCMP, a heterogeneous computing middleware platform. I am your host, Yassine Hariri, and my main focus at CMC is heterogeneous computing hardware and software. The co-presenter for this webinar is AJ Guillaume. He is the founder of Yetiware, a company specialized in providing solution and software stack to bridge the gap between software and heterogeneous computing hardware. He is also the founder of Yetiware and chair of the Kronos OpenCL Safety Critical TSG. So the outline for this webinar is as follows. I will start by giving you a brief presentation of CMC microsystems and a couple of slides to highlight the challenges with computing today, especially heterogeneous computing, and present some of the platforms, heterogeneous computing platforms provided and supported by CMC and how to access them. And this is the first part of the presentation. The second part is presented by AJ. We'll focus especially on this new product. It's a heterogeneous computing middleware platform product that is available at CMC. And this is based on OpenCL, so we'll be providing a brief introduction of OpenCL and then dive into the details of the HCMP software stack. And we will conclude this webinar with a live demo of the HCMP on the HPP, followed by a Q&A session where your microphone will be unmuted to allow you to participate. If you are unable to use your microphone, you can use the chat window to ask your question. So CMC exists since 1984. It is federally incorporated, and it is the creator and the manager of the Canadian National Design Network. And our main mission is to deliver core technologies in micro and nano innovation capabilities to every region in Canada. The National Design Network is a Canadian-wide collaboration project between 63 universities, colleges to connect 9,400 academic participants with 950 companies. And the main mission is to design, make, and test microsystems prototypes. CMC defines, develop, and manage Canada National Design Network. And here is some statistics about our community and clients. We basically deliver 5 key services to increase researchers and companies' innovation capabilities, including CAD tools and design tools, software, fabrication and services to create working prototypes, equipment and services for prototyping and testing, training and support, including webinars and training, and network management, including connecting and mentoring of clients. There's a brief introduction about the need of heterogeneous computing. As you might already know, the end of frequency scaling is, as a dominant cause of processor performance gains, has caused industry-wide shift to multi-core CPUs and heterogeneous computing systems. And this is due to the different obstacles that we faced during the frequency scaling, including power wall. We are not able to scale power. Instruction level parallelism. We can't extract enough parallelism from a single instruction stream. And memory wall. We can't keep up with the processor. And this is the main motivation why we shifted to multi-core and heterogeneous computing. The definition of it is the fact that we integrate different kind of processors architecture in one system. And this is motivated by the fact that the applications exhibit different type of behaviors. There are some applications that more focusing on control, such as searching, parsing, application data intensive, such as image, video processing, computer vision, and data mining. And computer-intensive application, iterative methods, and quantum simulation, other applications. And to have a gain in performance, we need to offload the right workload to the right processor architecture. And this is the main trend today, and we will witness more heterogeneity in the future. In this slide, I summarize heterogeneous computing in 3 parts. The first one on the top is the software application, and this requires a software stack in order to deploy the application to the hardware. And as I mentioned in my previous slide, we have an increase in heterogeneity. This means that in one system, we will have more than one type of coprocessor or accelerator. In this case, we show a multi-core host CPU, which traditionally run an operating system. And we have GPUs, FPGAs, ASIC, and maybe in the future, the integration of quantum accelerator in the system. And the main challenge today is that these accelerators come from different vendors and they have different APIs and different programming models. And it's not easy to write an application that span over multiple accelerators. So there is a lot of work on the hands of the software developers. And the need for a software stack and standards that allow people to deploy application easily to different architecture is something increasing. On the hardware side, we witness heterogeneity in two spaces. In the embedded space, in terms of system on chip, on our cell phone, tablets, and embedded devices, we have a system on chip, many core heterogeneous processor, big cores, small cores, DSPs, and FPGA that are integrated in one system on chip. On the other side, the HPC space, this is HPC, and we have servers in the cloud that offer to the clients accelerators such as GPUs and now more increasingly FPGA. And the main problem, as I said, is how to map the application to heterogeneous hardware. So this is a summary of a heterogeneous system architecture. I will just talk a little bit about the most commonly used accelerators today, and starting with the GPU. They were used for graphic long time ago, and they shifted to general purpose GPU to handle some compute intensive tasks in the scientific field. They are easy to program. They offer a single instruction multiple data architecture. They provide massive floating point computational power, lots of APIs. It's cheap for developers gaming and available in the cloud. These are the advantages. The bad side of it is that they are power hungry and they are expensive in data center and essentially no virtualization. And the ugly side is CUDA is proprietary. If you have a code that is written to target an NVIDIA GPU, it is not easy to just port it to GPU without optimization and without we have some noise in the background. I don't know it is caused by why, but if you are unmuted, please mute yourself. The next slide is the other side, is the FPGA, which is more available in the cloud and attracted a lot of attention in the acceleration space. And here I provide some good things about the FPGA. They are ultimate power efficiency compared to the GPU. Massive fine-grained parallelism, multiple instruction on a single data, and it is great for leveraging and accelerating storage and networking. And this is one of the main important advantages of the FPGA is the low latency when you choose a deployment model on a data center, for example, and you have an application that requires a low latency in the I/O, like video streaming processing or network processing. You can directly connect your FPGA straight to the network and process packets coming from the network directly without going through the host. And this is one of the advantages why FPGA is dominating in some spaces of networking. It is great at replacing ASIC because of the fine-grained reconfigurability aspect of it, and it also can be used to prototype a system on chip. And OpenCL is another advantage because a long time ago we were using FPGA with VHDL, so it wasn't really accessible to software developers who has no idea about the hardware. Now with OpenCL you can write a simple kernel and deploy it in FPGA like you do on a regular processor. The bad thing is it is difficult to find in the cloud. We have a few companies that offer this service, such as Amazon, and lots of IPs are available, but they are not for free. You need to buy them. Cheaper developer kits exist, but they are weak in performance capabilities and actually no virtualization. The main barrier is when I compile and synthesis time takes hours. This is something that vendors such as Altera and Xilinx are working on to make the compile time faster for these devices. This slide, for people who are not familiar or with OpenCL for FPGA, it describes the programming model for OpenCL on FPGA. Basically, you have the host side code of the OpenCL. It is responsible for managing the device or the accelerator, which is the FPGA in this case. And it's just doing sending data to the device, enqueuing task, and reading the results. So it's a management task on the host side. On the accelerator side, you need to write your kernel in a language, kernel language, OpenCL, and describe it. This is an example of an addition of two vectors. So, and you use the offline compiler, whether Altera or Xilinx, to translate your code in advance. This is why they call it offline compiler, because you need to translate your code to hardware. Then this hardware will be deployed by your host code. So this is basically the OpenCL programming model for FPGA. This slide summarizes the HPP. Many people are familiar with the HPP because we have deployed around 40 HPPs over the last 2 years. It's a heterogeneous processing platform in a single node. It has 3 types of accelerators, a GPU, Xeon Phi, and FPGA. And I think it's an ideal platform in order to experiment heterogeneous computing. We have also other variants of heterogeneous acceleration platform. The simulation acceleration platform, which is a combination between CPU and FPGA, and the MPA, which is CPU, GPU, or Xeon Phi, and HPP, which is a combination of both. So if you are interested in this platform, you can contact CMC to have access to it online, because it is available online. And the demonstration of the HCMP will take place using the HPP. There's another platform that is available, that will be available soon. It is on our roadmap. But this is a cloud computing platform. So the near term is traditional high-performance computing infrastructure to support CAD tools and HPC, and an experimental HPC cluster with the combination of CPU and GPU. So this is many nodes that that will be accessible to the researcher remotely, and they can experiment stuff like scaling up application using many nodes of CPUs and GPUs. Now, this is a transition slide between my presentation and the AJ presentation. And this is where we will introduce this new product, the HCMP. So the HCMP is a framework that's it's a middleware that's reduced significantly the complexity of developing application on a heterogeneous architecture. Complex tasks such as multi-device memory management, device IU, kernel scheduling, and dependency are already handled by this framework. And at the bottom of this slide, I show the HPP box. So we have multiple accelerators. And if you want to program this accelerator, you use one common programming model, such as OpenCL. But at the end of the day, you have different implementation for OpenCL, OpenCL 1.1, 1.0, and 1.2. And the difference between these implementation induce some problems in terms of compatibility when you need to port one code from one platform to another. In the right side, I have the software architecture for the HCMP. These are the layers that AJ will introduce in details. And you can already access this heterogeneous middleware online. And this is the CMC catalog entry with the link. So you have the definition of the framework, the challenges, and you can just request access and download it. There's a lot of documentations and reference design that will allow you to start quickly using it. Now I will hand it to my colleague, AJ, and he will be diving into the detail of the HCMP.
Hi, Yassine, thanks. Hopefully you can hear me.
We hear you, AJ. You need to share your desktop now.
Okay, perfect. Okay, so hopefully you can see the screen there. So I'm going to go over, and thank you, Yassine, for giving an introduction to the project. This is a fairly large project which has taken some time. So we're going to give a quick overview and a demo, and there's more to see, and you can reach out to either CMC or myself and we can talk in more detail about the details, and eventually we'll put some more detailed information up. So heterogeneous computing is a very interesting space, and the interesting aspect about heterogeneous computing is just why it's required. And I think that many in the development community are a little bit unaware of what's happening, so I just wanted to give a quick supporting evidence for what Yassine mentioned. So we talk about this gap between computing performance and what hardware can do, and software is essentially the problem. So this is a quick kind of motivation of what the gap really is that we did in collaboration with Cynet, the largest HPC site here in Canada. And we wanted to show just how much performance you can get out of an accelerator versus running a single core processor. So I'm not going to go through the experiment except for the result. So this benchmark, we wanted to show there's very little I/O. We want to hold everything constant except compute, and we want to show how much more computation is available from a modern system so that we can understand the gap between parallel performance and how developers generally write code today. So what you'll see is that if you are able to take a Python program, the numbers aren't here, but it took about 3 to 4 days. In comparison, using 3 GPUs simultaneously in the same workstation, we were able to get about a 31,000 times performance benefit. So there is this enormous gap. And a lot of the reason for that gap, exactly as Yassine mentioned, is clock frequency scaling. And I think that people don't really, I mean, this is kind of a shocking thing to show a developer, but what should have happened if the clock frequencies had increased, we should be up to 120 gigahertz clocks today. And that's not where we are, obviously. So developers still have this kind of mindset that, that the hardware is going to make up for performance. And hardware companies know what the issues are, and this is what's prompted heterogeneous computing, is really this knowledge of, in order to get more performance, we have to not only become parallel, we have to adapt our architectures, because there's not likely going to be one master architecture for some time that's best at everything. So instead, a GPU is well suited to certain tasks, a CPU is better suited to other tasks, and we have this type of mixture. And software, quite frankly, is not ready to kind of fill that role yet, and it's going to take some time for it to get there. So I want to give a quick talk about OpenSale, just a few quick bullet points. So when we look at a traditional program, it kind of looks like this. We've probably also seen these diagrams when you learned about operating system design or software design. So you write a program, and the operating system is kind of the mediator between you and the outside world. From your point of view, there is no other device attached. You don't even really understand what the processor is, you just kind of run. In the OpenSale world, what OpenSale does is essentially it exposes that there's other devices available that have memory, that can be managed, and that have unique characteristics. So by using OpenSale as a library, you can load it up and you can actually see that, oh, I have an FPGA attached, or a GPU, or a CPU. This kind of forces applications to take on the role that was traditionally held by an operating system. And this motivates the entire project that we did in collaboration with CMC, the HCMP project, because we were really saying to ourselves, can we take away from the application developer many of the complexities they're encountering by really thinking of how the OS normally handled this. And this is what you're going to see a little bit of today. So the key idea with, if we look at a homogeneous program, the entire program executes on the CPU. Absolutely all logic that's executing, whether it's the operating system or your program, the entire program runs just on one device, the CPU. A heterogeneous application, on the other hand, and you'll see this kind of arrow running to the right, is showing program order. So a program will start running on the CPU, and this diagram is a little bit confusing, but it's going to potentially take some work and offload it to an OpenSale device, and more work and offload it onto another device. And the CPU can also be programmed with OpenSale, so it's possible that you may actually use OpenSale to more efficiently write parallel code for the CPU itself. So heterogeneous applications are kind of odd in that you're not writing an application that runs on a single processor. Instead, your application is kind of a conductor of a symphony, where you have all of these different pieces running together at the same time. And this makes application development extremely challenging. So OpenSale, at the end of the day, is a specification for both parallel and heterogeneous computing. It's implemented by vendors to support their processors. So if you have an Intel piece of hardware, you will likely get an implementation from Intel. NVIDIA, you'll get it from NVIDIA. AMD from AMD, and so on. OpenSale contains this common set of abstractions that are then mapped to particular hardware by an implementation. So one way to look at OpenSale is as a hardware abstraction layer. So what does that mean? It's no different than looking at anything else that tries to insulate you from how hardware really works. So we have kind of this idea of how hardware works, that's called OpenCL, and then particular implementations will map that to real systems. And essentially, they use OpenCL as pretty much the only mechanism to get access to heterogeneous processors. So CUDA does exist, and CUDA is really standard for programming NVIDIA GPUs. OpenSale is the only standard that really works across the board. Vulkan does have compute capabilities, but that's really only targeting GPUs at this point as well. So OpenSale is kind of this universal approach that the industry has gotten behind today. So one of the things that comes up with having a common abstraction is that you kind of miss the mark. So this diagram showing you this kind of set of, for each device, the things that the hardware can do, and the things that the OpenCL specification, this dotted line, can't actually capture. It doesn't express it. So essentially, every hardware vendor that came to the table gave something up by supporting OpenCL. And it's not a bad thing. It's just that if you had an application or had a programming model that was exactly an FPGA, you probably wouldn't be able to run it on a GPU or on a CPU in a way that was efficient or meaningful. So what happens is that vendors come back, and you'll see this little chart here at the bottom is called vendor extensions. So there really are good reasons why you'd want to support a particular feature on a GPU or a CPU or an FPGA. And extensions are used to provide access to tap into that unique hardware characteristic. So what this diagram showing is that the OpenSale standard can't possibly fit every piece of hardware. If a vendor sees that there's a compelling reasons to support something that's not otherwise supported, they'll do it through a vendor extension. So OpenSale itself consists of two parts. So sometimes you might see a presentation of OpenSale and kind of get confused in terms of what actually is going on. So think of it as almost like programming a network socket, something like that. There's the host API, which is a classic C header and shared library. They just link to it. It's OpenCL.h and libopenCL.so, and use this host API to detect, initialize, and manage OpenSale devices. So this is your C application or C++ application uses this to get at the device. No different than opening a socket gets you at the network. Doesn't do anything yet, it just allows you to control it. The other part of OpenSale is a device kernel language. So this is used to write kernels, which is the buzzword for programs on the particular device. So supported today is OpenCL C, OpenCL C++, and SPIR-V. And they're not all supported in the same way in the same places. The project that we're talking about today specifically tackles the first part of OpenCL. So what is that? The goal of this project was to eliminate all problems that I'm aware of with the host API and really shore it up for enterprise software development so it's ready to go. Future projects could tackle how the kernel languages themselves are written, and that's a topic that we can potentially talk about in the questions. So when you look at OpenCL itself, this is the host view. You have this header file, OpenCL.h or CL.h. You then have a library. The library doesn't actually do anything. The library is just a proxy that gets to actual implementations. So this way you can link to a single library called the ICD, and then this will then get you to an implementation from all the different vendors. And if this was not done this way, you'd have to link to a particular vendor implementation. So this is the ICD, and this is these are the pieces you need to know to talk about the context of this project. So the OpenCL host API is a little bit complicated. So to date, there's 6 versions of OpenCL in the wild. There's 1.0, 1.1, 1.2, 2.0, 2.1, and 2.2. 2.2 is not yet in the wild, but it's standardized and will be out there at some point. OpenCL has 2 profiles, the full and embedded profile, and it gets more complicated because there's about 100 extensions. So these amendments to the specifications where I said that there's a good reason why you want to use a particular feature from OpenCL for that particular hardware. For performance reasons, you really want to do that. And that is the extension, but it does make it passes the burden on to you as an application developer to use these things efficiently. The other complexity is that implementations may interpret the specification differently. So it is entirely possible that even though you're writing similar code, you have to write a slightly different flavor based on how the vendor interpreted the specification. This is generally something that can be addressed by the OpenSale working group, but it is something to be aware of that in practice there can be different interpretations, which results in you having to take on the burden of how to handle that in your code. OpenSale also does not have a stable API. Essentially what this means is that if you ship an application for one version of OpenSale, there's no reason why it won't break for a future version, which makes software engineers a little bit spooked when you're trying to ship something in production. And when customers expect it to run for a long period of time. The other aspect of the host API is that how you efficiently dispatch jobs is different per implementation. There's good reasons for that. It's not necessarily an abstraction problem, but it does mean that essentially the way that you write code, if you want to work on everything, you're going to have to write host API code almost per implementation and per vendor. You can use a lower subset that will kind of work, but if you want peak performance, this is the barrier of entry. So this is where we came at when we talked with CMC and the project kicked off. These are the issues, and this is how we're going to solve them. And we're going to take a quick minute to talk about how projects basically run today. How do OpenCL applications look today? So today, if you write an OpenCL application, it kind of looks like this. Your application will, if it wants to have the broadest possible support, have inside of it logic for OpenCL 1.0, 1.1, all the way to 2.2. In practice, very few applications actually do this, but to be completely conformant to the specification and work on absolutely everything, this is the barrier to entry. This is what you'll have to do. So you'll notice that you have to write kernels, which are your device programs, per implementation, and the host logic is also going to be different per implementation. This all then links to the ICD, and this is how applications look. Now, if you are a particular vendor or software vendor who has a stake in OpenCL. I mean, Adobe uses OpenCL. We see TensorFlow, I believe, has some support for it. If you're building some sort of application, what you'll generally do is be a little bit more clever. So you might take out the host management and put it into a singleton within your application so that you can say, well, I'm going to write something that tries to work with OpenCL in a unified way, because otherwise it's way too complex within your application. And there are many pieces of OpenCL that are very device state specific. So allocation of memory, if one module allocates memory on the device and another module doesn't know about it, you may hit all sorts of strange conflicts. So you really want to have one central place where everything is managed about these devices. And the way you'll generally do this in software engineering is introduce a singleton that manages that state for the entire application. What we're doing is we're kind of pushing that down the software stack here so that we can basically make a method of accessing these devices or a middleware piece that you still are going to write your kernels in every single version, because as we said, we're only tackling the host API in this project. But what we are doing is taking the complexity of writing host code away from you so that we can manage in this layer how we actually treat every particular device. We can add in implementation specific features if we have to. If there's an extension that we should use, we will use it there. So you don't have to care about it. This way we provide a lot of the advantages for you to be able to run on any device as you wish, but you still have to write at this point kernels in a higher level in OpenCL or so on, and that is still version specific. So over time, what we envision for this platform long term is to be able to not only support OpenSale on the back end here, but potentially standards such as HSA or Vulkan. I even go so far as to say that it's possible to support CUDA if there's an actual need for that. And what you see in the top diagram there under user applications, what we really want to do is have you ship only one set of kernels. Doing that in practice is extremely difficult, and that has to do with performance portability, which it's a whole other talk to get into that. But this is long-term where we want to go. So where we are right now is this situation where it's a lot easier to get started with OpenCL. It's a lot easier to work with it, but over time, we'd like it to be even easier so that you're not duplicating effort at the kernel layer, which again, you do have to do today. The architecture, so HCMP, Heterogeneous Computing Middleware Platform, is really kind of a code word for the entire stack end to end. It's always tricky to introduce, we want to introduce a term that's like operating system or like OS, but really is for heterogeneous computing. So feel free to take the term HCMP and apply it anywhere you wish. If you think that's an interesting term, maybe it'll catch on. So we're just one example of this. Our application stack kind of looks like this. Clean itself is built on top of these other components, Clay, which is built on top of OpenSale and libhc. And most of this presentation is going to talk about the highest level layer because that's what's most interesting. And a few slides are going to talk about what's underneath. And I'm happy if anyone wants to reach out after this presentation to me, we can talk about it in some more detail. So we're going to start talking about Clean by talking about its goals. So I want to provide a very simple user interface to developers to load, compile, and run kernels, allocate memory, and to accelerate applications. We want the application to be able to leverage Clean internally to have an adaptive scheduler so that Clean will manage memory I/O, and kernel execution. So the key point of Clean here and the key contribution is to provide an interface that developers will like, but allows really efficient scheduling and management of devices and leveraging vendor extensions or KHR extensions as it can internally. We also want to provide high-level primitives for common operations. So eventually we'll provide support for streaming data. Right now, the execution model isn't aware of what streaming is, so the scheduler is not going to do a very good job at it. But at a higher, we can add a higher level primitive that understands what streaming data is, so that the scheduler can work with that. And that's actually something I'm working on as a side project right now. The important thing to note about Clean is it only runs on a single system with multiple devices. It does not run on a compute cluster at this point. You can make it work in the same way that you can use MPI to work with OpenMP, but at this point, that's a constraint of the project, is to work on a single system with multiple devices. Otherwise, we have to start thinking about fault tolerance and consensus and all these types of things. The other aspect of Clean that makes it a little bit unique is that we're supporting bindings for many languages. So although I like C and C++, there are many developers who would benefit by using the exact same framework if it was supported by Python and Java. And that's something that we've designed from the get-go, is not only to support the languages that we like, but to allow other languages to pick up and reuse the same component. So in terms of architecture, Clean itself is not a replacement for OpenCL, C, or C++. I mean, we don't try to provide you with something like single source along the lines of Khronos' other work product or specification SYCL. We don't try to do that. We try to work with you to make OpenSale easier to use rather than wholesale replace or hide these languages. So the main point is to reduce the host code complexity. The form that Clean takes is it's a shared library with a stable C ABI. So this means that if you write an application today, we are guaranteeing that it's going to work 2 years from now, 4 years from now, 5 years from now, 10 years from now, even with the industry being in a state of flux in terms of which standards is even going to survive. I mean, maybe in 10 years, OpenCL has kind of given way to Vulkan or to HSA or to some other standard. So we have to build in mechanisms for how that's going to work. And you'll see a little bit of how we accomplish that. So the way to think of this, and what we thought when we were designing this project, is to think of it as a heterogeneous operating system provided as a library. So at the end of the day, it's just a shared library, but we're using OpenCL as a hardware abstraction layer so that we can manage these devices, and the application that then is written on top is insulated from a lot of changes in the as standards and so on continue to grow and adapt. So the main idea here is that when there's a new OpenSale version that's released, you can upgrade Clean and automatically get support for it. Now, as I said, the kernels are specific, but if you think about it, kernels are also generally backwards compatible. So if we suddenly supported OpenSale 1.2, if we went back in time and 1.2 had just been announced, we'd be able to use the OpenSale 1.2 runtime, and the kernels will still be accepted by 1.2, even though they're written in 1.0, 1.1. The issue with OpenSale has traditionally not been necessarily the kernel language being kind of, let's say, volatile in terms of changes and deprecations. Most of those changes have really been focused on the host, and that's what this project is there to address. Internally, we use this Clay project, which is essentially just C++ bindings, and we'll talk about that to build Clean. And then this in turn builds on top of libhc, and you'll see some of what's under the hood a little bit later. So internally, what does Clean look like? If we take away the covers of Clean, we pop the hood open, what do we see? So at the highest level, you see you have a user application, which will use the C++ headers we provide for Clean. You can also provide other language bindings, and support will just be as good as what we provide. There's no need to just use C++. Internally, we have a C ABI, which then maps to, we have something here looking from the left, the ABI bridge, which is just mapping internal to external types so that the ABI is really simplified. We have logging, profiling is supported within. We have something that manages programs, devices, memory, and the largest and most complex component by far is a scheduler. So the scheduler is adaptive. What this means is the scheduler is going to look at how the memory system is actually operating, and is how work has actually been dispatched to Clean, and will try to use heuristics to do a better job. So the very first scheduler shipped with the HCMP is relatively naive but safe. We do have a mode that you can activate that will turn on experimental schedulers because we want to make sure that our scheduler is 100% correct over time. So we kind of have two modes. There's experimental version that you can turn on, which should be faster, but there's the safe but reliable version, which is always enabled by default. And we expect that active research is going to be done in scheduling over time as we find opportunities to do better and better jobs with better heuristics. So here's your first taste of what clean looks like. Ironically, one of the most difficult applications to write in a manner that's actually portable is CL info. And if you try to write it, actually, you'll get a little bit frustrated just because of how you have to handle which versions on the system. ICD issues come up very quickly, header file issues come up. So this is a complete example of how CL info looks for clean. So what you'll see here is that you can get a vector of all devices on the system. Clean internally will initialize devices and do everything as it needs to do to get them ready to use. If there are no devices on the empty, if there are no devices available, it just says no devices detected. Otherwise, it's going to loop through every single device, print a short description of what that device is, and it returns this kind of property thing that I'll talk about in a moment. And it will recurse down and look at everything that's known about the device and return that. So normally you see, normally you have in OpenCL these CL get info type of queries. These have all been replaced with something a little bit more dynamic, and you'll see that. So all of clean is really about programmer convenience. And that's how come as well, we kind of support XML out of the gate too. So you actually can get back at a formatted XML string that gives you all of the information about what is known about the device. And this is going to be really useful for web services or things like that. And we'll show a demo of this running. But this is your first taste of clean and what it looks like. So this property interface, that root property I mentioned, I'm going to go through kind of a few pieces of clean and then we're going to get into the demo. So clean objects have properties associated with them. This is really influenced by XML DOM, JavaScript, something like this, because the queries, the properties actually change over time. And rather than being a hard failure because you do not know what the property name doesn't match, which is the case in OpenCL today. So if you query for a property and it doesn't exist, you'll get basically a compiler error. So instead we've shifted that to runtime. What it allows you to do is to basically do queries to say, okay, well, do you have shared memory? Well, how large is your SVM memory allocation? If you don't have it, you just get an empty result. And that allows you to be a little bit more graceful in your failure. So you'll see this a little bit in terms of how you'd actually do that in application. It makes it a little bit easier to do graceful failures, which allows you to query for properties and be independent of the OpenCL version. The interface returns metadata along with the properties. So it actually will tell you how much data was returned, the type of it, and this is really designed to make your life easier if you are looking for interesting properties. We'll show that. And you can do recursive searches for it. So you can search for properties that say something like memory. And it replaces the need for complex CL get info calls. When we talk about kernel loading and compilation, so how do we actually load kernels into clean? How do we compile them? And you're going to see demos of all this. So we know that the future of OpenCL is SPIR-V. Right? This is something that Kronos has been talking about. And we know that OpenCL C++ has already built its targeting on top of SPIR-V. So for consistent abstraction, we kind of view all device code as an IR. So we actually will call OpenCL C 1.0 an IR. And you'll see that how that kind of works when we go through how the classes look. So right now, out of the box, we support OpenCL C 1.0, 1.1, 1.2, 2.0, and 2.1. There is no OpenCL 2.2 so far as I know, so we can't really support it. But we support SPIR-V and we support SPIR. And what's interesting to note about this is that you do have to use extensions, for example, to get SPIR-V support on OpenCL 1.2. It's not always available. So we, out of the box, support things just working, and you'll see a quick example of that. So the basic usage pattern is that you're going to query a device to see whether or not your IR supports, whether or not the device supports the IR you want, and then you can load it up. Memory management, we're going to talk about that quickly. So in OpenCL, memory is generally associated with a particular device. So you'll say allocate a 1 GB buffer on that GPU or on that FPGA. So with clean, we do a little bit of a trick. You actually allocate it without any particular device. You just say, give me a gigabyte of data. And internally, clean doesn't have to actually know where the data is bound or move it around or actually force an allocation, which can be slow. Instead, clean tracks what kernels operate on particular memory objects. And because it does that, it can optimize memory movement. So if you are working on, so we'll talk about that when we see the scheduler, how it actually works. So the way you get data back out of clean is using a future object. So there's all sorts of complicated synchronization rules inside of OpenCL that you have to obey, and we sidestep all of them by just knowing that clean is operating entirely on the data at once, and then if you don't want that to be the case, you're going to you're going to pop the data out using a future object. So the general idea is that we're enabling the scheduler of this abstraction. So internally, what clean does is it constructs a memory I/O plan. So internally, it's going to record what memory you want to allocate, that you want it to fill it, that you want these kernels run in this sequence. And it depends upon the scheduler, but it can actually wait until you've requested memory that required that memory to have actually been consistent. So it can work backwards and figure out what needs to be done. So internally, there's actually an IR just for how to operate memory, how to prune memory, and how to better schedule it and resequence plans. That's all inside of clean, and that's done in a way that then maps eventually to command queues on particular devices. So our general goal is to fill command queues as large as we can. So what we want to do is, in order for a device to be kept busy, we want to have these big, deep, long command queues. And the more work that's in there, the better the device is going to operate. So this kind of notion of clean being in charge of memory is a trick, because it allows us to accumulate results for what kernels need to dispatch and then enqueue a large set of work all at once. This model is going to work well for things like simulations that are time-stepped. It's not going to work well for things like streaming. And that's how come I mentioned that a streaming kernel would require special support. We can resequence kernels, but only in the case that there's no memory dependencies. So if you have this case where you have two kernels that need to run, one requires a gigabyte of data, one requires a megabyte of data, and you don't quite have enough space, depending upon what's resident on the card, if there's no dependencies, the clean can resequence for you. Okay, and we can automatically use KHR and vendor extensions for fast I/O. Okay, so let's take a look at clean. Let me just adjust what window's being shared. Give me a moment here. I just have to change this. Okay. Just one moment here. Change this. Okay, so here you can see this is the HPP. We're logged on here. And we'll show you quickly the device info query. Okay, so this source code is going to dump out everything known about each particular device. There's going to be a lot of data. On this particular system, there are, I believe, 4 or 5 accelerators. I don't remember the count. So to use clean, we include clean.h. As you saw, we get all the devices. And we're going to print out a short description. And then this is going to show a text version, not an XML version of what the device actually looks like. So if we run, so this command HCMP CC, all it is regular G++ or Clang compiler. It's just there's a bunch of linking flags. That's all it is just has the extra linking flags to make it easier. There's no single source or special compiler required. This is just for convenience for researchers to not have to type in all of the flags. So we run this, you're going to see a lot of data. So what this is doing is this is outputting absolutely all device properties and information for every device in the system. And the reason we add, so you'll see that we actually put in descriptions as well for what's in here, so that if you're just learning OpenCL or you're just learning to play with heterogeneous computing, you can kind of poke around and see what kind of interesting data is available to you if you can use it for your application. So I'm just going to change this here to be show a list of devices. rather than show all the properties. The properties actually do form a complete tree, and that makes it easier for us to group things together. Okay, so you'll see that it's detected 4 systems, 4 cards in here, and this is what it ran on. In this case, they're actually all running on the same OpenCL version. That's not required. That just happens to be what is installed on these machines. So that what I showed you will work for every version of OpenSale, including 2.2 support is there, even though there are no implementations in the wild. The other thing to note is that we can get this nice little log here. So I turned on logging, and because we're kind of inspired by the idea of an operating system, we can actually get a dump of everything that was done. If there's any warnings in the system, anything that went wrong, and we can see basically, I use this all the time for debugging. We can see exactly what happened as it executed. You can also get dumps of how the scheduler did its work, and you can get that. You need a special license for that from CMC, but that is available to you as well. So in terms of just having a program that's going to take this kernel, that's just going to add 1 to a list of integers. It's pretty straightforward and simple. What we do here is this typed memory array is going to allocate some data within clean itself that's not bound to a particular device. We're going to fill with zeros. We then will create a OpenCL C 1.0 IR using that string. You can load it from a file directly. There's all sorts of input mechanisms already support it for you. As you saw, it gets a collection of all devices. And we're going to try to load the IR on every single device. If you can't load the IR because there's a compiler error or something like that, it'll tell you and we'll stop, because we check here for the load status. And if there's some issue, it'll give you the log. We extract the kernel, which is, again, basic OpenCL kind of mechanism. And you'll see here that we run this kernel on this data here. Let's see if I can highlight it. In, right? So what's actually happening in the background is there's only 1 buffer. But if we run this on 6 or 7 devices, we've actually executed in a for loop to run on each device 1 by 1. So Clean is going to have to move the memory around for you. And if there's an option to use a particular vendor extension or other mechanism to transport that data, it'll do it for you automatically, depending upon how the scheduler thinks is optimal as well. Eventually, we get a future object back. They'll return to us the result, and we can print the data out. So we can try this out. Okay, so there you can see that it ran. So because there's 4 accelerators, each one added 1 to his initial 0. It's not the most interesting demo per se, but it is showing that the memory is automatically being moved around as required to maintain consistency. I'm going to go back to the presentation and finish that up, and then we will have our opportunity for questions. So let me just adjust here. Okay. So that's Clean. It's a quick real run tour. There's a few other features in there really interesting in terms of how to actually deal with vector types, and all that stuff is all baked in. At some point we'll do, there is a white paper as well you can get from CMC, and stay tuned, more demos will come out to show you how the architecture works. So Clay, we're going to show you some of the other pieces. Clay provides idiomatic C++ bindings. That's what Clean is built on top of. The Chronos C++ headers are compile time only, which does lead to, let's say, some issues. And you also see that with things like boost compute. There have been a number of bugs that if you had only been compile time only, you couldn't have worked around. So we're quite proud that we were able to work around some bugs that were discovered later on in only a handful of lines of code. And we can talk about that if you're interested during the Q&A session. So Clay provides idiomatic C++ bindings. It's exception safe. There's no external dependencies outside of the C++11 standard library. And internally, it's actually built on top of another thing called libhc. If you request the white paper, either from myself or from Yassine at CMC, we can go through these details. libhc is a different component. So libhc is a little bit of a confusing component to explain. I'm going to explain it very quickly. And libhc is an API for what heterogeneous computing is all about. So we don't know if another standard will replace OpenSale. But what we do know is something like OpenSale will always exist. And we can use this knowledge to try to abstract what heterogeneous computing is from the particular standard. So what we did is we planned for obsolescence in advance. Hopefully it doesn't happen, but if it does, we have we're ready for that. So we also fix up all the Kronos OpenSale header files. That's another kind of topic. But we've replaced the OpenSale ICD, and we've migrated libhc to a capability interface. So we've taken OpenSale and said, well, we're going, instead of looking at extensions in one fixed kind of architecture, let's just look at it as a set of capabilities or buffet model. And that's what we've done in this project. So the whole point of libhc, we can give an hour talk just on this, is that all calls to the heterogeneous, to any heterogeneous standard pass through this. So we have a single point that intercept calls and remap if we have to. So if we wanted to implement OpenCL on top of Vulkan, we just have to intercept and then change how those calls are made. Future modules can be provided to support new mappings. We can talk about that, how future proofing is accomplished. And the whole point of this is software stability, so that anything you write will continue to run over time. Just as a teaser, a lot of the motivation for this from our work with CMC is to allow you to do API call forwarding over the cloud, so that essentially you'd be able to write an application that can forward these API requests to a remote system, so that even if you don't have an FPGA or GPU or something, one of these expensive devices in your system, you can forward your requests across the internet and try one out, but with a lot of latency, just so you can see what it's like. Okay, so I'll end my side of the presentation there. If you have questions or comments, feel free to reach out. There is a white paper available, and I'm happy to dive into more details one-on-one with anyone who's interested in this part of the project.
AJ, this is Dennis. Thanks for the presentation. Your last slide there, you said you replaced the ICD. Why was that necessary?
Hi, Dennis. That's a longer, I can give you, let me give you the 30,000 foot view. And then we can talk about that in more detail. So you can hear me hopefully, right?
Yes.
Okay. So the 30,000 foot view of why we had to change the ICD is the ICD is not really, is not version compatible, right? So the ICD, the spec doesn't version, but if I were to say build an application that linked to the 2.0 version of the ICD and then ship it to a client that only had 1.1 installed, it would break at linkage time, right? So that's part of the reason why we had to adjust it. The other reason is because I have in mind that I think OpenCL should be based on capabilities. The ICD doesn't really fit with that abstraction. Does that make sense? So there's some deeper parts we can get into, but that's part of the motivation.
If the assertions are true, it makes sense, but I'm not convinced yet that they are, but we can take that offline.
Yeah, I'm happy to follow up with you in a deeper discussion on that.
AJ, I have a question on the chat window. Someone asking about the ABI. Can you give a brief explanation of ABI and how it's used in the HCMP?
Okay, yeah, I didn't see that question. So an ABI is essentially an application binary interface. So we're all familiar with an API, something like printf. Here's how to write code and here's how it should look, right? But an ABI is saying the types have to be a certain size, functions have to always look like this. So you can have an API that can change how functions behave over time, and that's okay. But an ABI says printf is always going to look like this. And once it's fixed, it doesn't change. And that's how come you can run old applications on new software platforms, is the ABI doesn't change.
We encourage you to ask questions either using your microphone or the chat window. Is another question, AJ, is the IR interrupt routine?
Yeah, so I just saw that in the chat window. The IR, so I guess I over acronymed you, was the intermediate representation. So think of it as almost like, I want to use the word assembly language. It's basically how the compiler represents a program. Of course, OpenCLC looks like an actual language. So that's how come I said we're kind of pretending that it's a description of something else just to be forward compatible with SPIR-V, which is an actual IR, and just you would never write a program directly in IR. It looks like assembly language. So hopefully that answers the question.
So here's the comments on the chat window. HCMP can speed up deep learning for large data sets.
So I will say that the HCMP is a project that allows you to get easier access to these devices. It's something that, for instance, TensorFlow would use. The whole point of this project is to make it easier for you to get going. And let me comment on the deep learning thing just very quickly. If you look at machine learning, it's a combination of two really hard things. People who are experts in machine learning, right? But that's already a rare skill set, you know, deep neural nets and all these things, and experts in parallel programming and GPU programming. And generally what you see is only the big companies do this because they have expertise in maybe one, but not the other, right? So the thing to take away from this project is that we're making it a lot easier for you to write applications and get started so that you can figure out how to write your deep neural net frameworks. If you want to implement one on top, you're more than welcome to chat with me on how that could be done.
We have another question. What is exactly Clay?
Okay. Yep. No, I think I kind of did the whirlwind tour here. So Clay is a layer of C++, C++ bindings. I think the best thing to do maybe is to reach out to Yassine for the white paper because it's described in detail there, and I kind of was fuzzy here. Essentially, Clay is just a idiomatic C++ 11 bindings for each OpenCL version, and the paper will discuss it in some more detail.
Okay, so we have 2 minutes for another question or two. Meanwhile, I would encourage everybody to go and download this framework and try it on your HPP or on any other heterogeneous system. This is a very good and exciting time. We encourage your feedback in order to improve this framework because it's based on the bugs you are reporting. We're gonna make it more reliable to use in many spaces. Another question popped up in the chat window. Yes, the slides will be available as well as the recording after this webinar, and I will contact everybody to access them. How will HCMP prepare for single source OpenCL SPIR-V eventually? This question is for you, AJ.
Yeah, no problem. So there's two parts to that question. One is single source, and one is using SPIR-V. So HCMP is not designed to tell you how to do what you want to do. If you'd like to make a single source, so HCMP, think of it as something like an operating system. You can build whatever language you want on top. If you'd like to build a single source solution in Python or C++ or even implement SYCL on top, you can do that. There's nothing preventing you. And so we are not doing it ourselves on purpose because we want to enable kind of innovation in the language space and application space. So what you would do is you would build something on top, but it would not be nearly as complicated as implementing something like SYCL by using the HCMP because the host API part is a lot simpler. We do support SPIR-V out of the box if SPIR-V support it. As I said, we haven't tackled the kernel language aspect of this project. That would be a second project, but if you're interested in doing single source stuff, you can reach out to us and you can directly use this. It would be easier than doing it a different way. And I will say that one advantage of doing it on top of HCMP is it'll work with any version of OpenCL, whereas SYCL is only working on particular versions.
Okay, thank you, AJ. I think we are at the point to conclude this webinar. I would like to thank our presenter, AJ, and his company, Yetiware, to participate in this project. I would like to thank everybody to take the time and attend today. There will be a recording available to you, and I encourage you to go and download the HCMP and try it. And for any question, you can contact either me or AJ. Thank you very much and have a good day.